Hello. In this video, let's talk a little bit about static CMOS gates. So static CMOS, as you all know, is one of the most popular design styles and offers multiple advantages, primarily being robustness, they're fast, energy efficient, and they're easy to design. So let's look at a few tweaks that one can do on the basic static CMOS to optimize designs for specific purposes. So if you think about a static gate, let's take an AOI 21, for example, as shown here. Now, we looked at sizing and we said when you want to do transistor sizing for such a gate, we'd size it such that the worst case pull up or the worst case pull down both have equal resistances, and this resistance is going to be equal to that of the smallest inverter in the technology. So therefore what happens is with that, you essentially get the size of the PMOS transistors to be 4, 4 and 4, because in the worst case, the PMOS is a 2 transistor tall stack. Similarly, the NMOS, the A and B NMOSs are connected in series, and so they are sized to 2, whereas the C NMOS transistor is sized to 1. So if I now look at the logical efforts at the individual inputs, the logical effort is nothing but the ratio of the capacitance at the input compared to that of the unit inverter. You see that inputs A and B have a logical effort of 2 because they have a net capacitance of 6, whereas the C input has a logical effort of 5/3. And if I just look at the nominal parasitic delay, basically ignoring any capacitors which are in the stacks, you see that the nominal parasitic delay is 7/3. So in this gate, you see that inherently this gate is asymmetric. That is, we have an input which is faster than two other inputs. In this case, GC is going to be a faster input compared to inputs A and B. And so what we try to do is when we design a CMOS of this fashion, we'll try to design it such that the parasitic capacitance at the output node is less, and hence instead of keeping A and B near the output node, we'll keep them far away. That way we reduce the net capacitance at the output node. Now we also looked when we discussed NAND gates about the input ordering effect. Right? So nominally again, we know that symmetric gates, if you look at NAND gate, a NAND gate is going to be size 2, 2, 2, 2. So nominally the NAND gate has equivalent or equal logical efforts for inputs A and for inputs B. Now we know that in reality, however, they're going to be slightly different. One, we definitely know that the parasitic delays are going to be different for different transitions. And two, if you look at transistor A and transistor B, the NMOS transistors, when they're sitting in the same well, both the substrates of the transistors are going to be connected to ground, which means that A is going to have a VSB compared to B. In B, both the source and the substrate are grounded. Whereas in A, if it's sitting in the same P well, then there is going to be a slight source to substrate voltage difference here, which is going to lead to a slightly different drive current associated with A as compared to B, which gives us the fact that the logical effort at A is going to be different from the logical effort at B. Additionally, we also know that the delay depends on which output switches in the series stack, right? So normally what we do is we define something known as an outer input and an inner input. So remember, the output of the gate is this node. So the input which is closer to the output is known as the inner input, and the input closer to the rail, to the ground rail, is known as the outer input. So in this case, we have the innermost input, which is A, and the outermost input, which is B. Right? Now what we know when we looked at parasitic delay of the NAND gate is that the delay is smallest when the inner input switches as opposed to when the outer input switches, because when this switches, the intermediate node capacitances come into play for parasitic delay. And so this essentially tells you that when an input arrives at A, it is going to switch faster than when it arrives at B. And so therefore, if you're going to size the transistor, you're going to size it in such a way that you'll take advantage of the fact that A is a faster input. Now let's look at another example where we want to design an asymmetric gate. So again, nominally symmetric gate can be made asymmetric in certain conditions. So here let's look at an application where we have a control signal which is a reset signal, and depending on the value of this reset bar, y will either follow a or y will be independent of a, right? So when reset bar is high or when reset is 0, the output has a logical answer, right? And so if we want to, so normally when we use a setup like this, right, we normally are going to send the reset signal first and then send data to it. So it's almost always assured that reset will arrive much before this input A. So if I know that is the condition in which this gate is going to work, then I will try and optimize this gate in such a way that I can probably speed up the response to input A by trading off the speed for the response at the reset bar. Right? So if you look at the NAND gates, first thing we know is because we want the delay of A to be quicker, we'll size up the NAND in such a way that the reset bar is sent to the outermost input. So hence reset bar is connected to the NMOS transistor that is closest to the rail. Now, how do we make an input fast? One thing we can do to the input is we reduce the input capacitance. So if you reduce the input capacitance, you reduce the logical effort, and so hence that input becomes fast. And the other way you can speed up the gate is by reducing the capacitance at the output node and reducing the nominal parasitic delay. So we'll use these two techniques on this gate. So what I do is when I'm going to size up the gate, again, I want to make input A fast. So when I size up the NMOS stack, I'll size it up in such a way that I will trade off the size of A to the size of reset. So here if you look at this condition, if I look at the pull down resistance, the pull down resistance of this transistor, which is sized 4, is going to be R by 4, and the pull down resistance of this transistor, which is sized 4 by 3, is going to be 3 by 4. So in pull down, the resistance is the same as that of an inverter, which is R. However, the logical effort at A is going to be substantially reduced because the input cap at A is 4 by 3 and not 2 that is normally used in the NAND 2 gate. So this way we have reduced the logical effort at input A by increasing the logical effort at the reset bar input. The second thing we also do is, because we don't care about the reset bar, or rather we are okay if reset bar is a slow input, what we do there is we'll also reduce the pull-up size of the reset bar. And by doing that, what happens is that the net parasitic capacitance at this node is also reduced. So hence what we get is, we get the logical effort for input A to be 2 plus 4 by 3 divided by 3, which works out to 10 by 9. Remember, the logical effort for a NAND 2 gate, which was sized symmetrically, is going to be 4 by 3. So here you have a logical effort which is much less than 4 by 3, it's close to 1. And you also have the parasitic delay which is reduced at this input. So if I look at the parasitic delay of this gate, the parasitic delay of this gate is given by the net capacitance at this node, which is 1 plus 2, 3 plus 4 by 3 compared to 3, which is 13 by 9. Right? Again, the parasitic delay of the NAND 2 symmetric gate is going to be 2. So we have substantially reduced the parasitic delay. Right? So two changes have been made. We have reduced the size of this transistor and we reduced the size of the reset transistor. So technically I can keep improving the logical effort of A by making the reset bar transistor wider and wider and by reducing the size of this transistor. Right? And so eventually, if you size the reset bar large enough, eventually the logical effort of A is going to be close to 1 in this case. Right? And so you see here that you can trade off logical effort at one input for the other input. However, at some point what's going to happen is that the area associated with the other transistor is going to be much larger than the gain you get from reducing the delay. Second thing is, when we do designs like this, we automatically assume that reset bar is not in the critical path of the circuit, right? But as you keep increasing the logical effort on this node, there is a chance that at some point this might creep up in delay. So care must be taken to ensure that when you size these transistors, you size them such that A still remains in the critical path and reset bar still remains out of the critical path. Now let's look at gates if I want them to be symmetric, right? So sometimes we want gates to be symmetric at multiple inputs. And that means the gate should look perfectly alike when I look at either of the inputs. And as I discussed before, the NAND to gate is not symmetric simply because the two transistors don't have the same bias conditions. And this normally involves a trade-off with power and area. So an example of a NAND 2 gate that is going to be completely symmetric to A and B looks something like this. We have two gates connected one after the other, and if you look at the sizing of the gate is the pull-up transistors are both 2 and the NMOS transistors are all sized to 1, 1. Now if you look nominally at the total gate area in this gate, it is going to be exactly the same as the NAND 2 gate. However, because there's so much more wiring and so many more contacts in the structure, this structure is going to be larger than a compact NAND 2 structure. However, in this structure, you see that both inputs A and B see exactly the same configuration. So, in all ways, A and B are matched to each other, indicating that they're going to be symmetric inputs. So, no matter where the input comes in here, both are going to have the delay from A to Y is going to be the same as the delay from B to Y. Now, we can also size the gate such that one particular transition is faster than another transition. For example, I can size it such that the high to low transition is faster than the low to high transition. So such a gate is known as a skewed gate. Now what happens in such a gate is you change the design such that one of the two delays is reduced at the expense of the other delay. So a design that favors the output rising is generally called as a high skew, and the design that favors falling output is known as the low skew. So if I look at a normal inverter, the smallest inverter in a technology that we've been discussing in the class has been 2, 1. So the pull-up logical effort for the pull-up operation is 1, the logical effort for the pull-down operation is also 1, and the average logical effort is 1. Now suppose I consider a gate where I've sized the PMOS to be 1 and I've sized the NMOS to be half. Now is this gate a skewed gate? It is not. If I compare these two gates, both the gates have same. So in this gate, the pull-up resistances are, the pull-down resistances are. So both the transitions are equal. Again here, if you look at this gate, the pull-up resistance is 2R and the pull-down resistance is also 2R, indicating that in this gate too, the pull-up and pull-down delays are going to be equal. So this is not a skewed gate. What this gate is this gate is a slower version of the inverter. So when I talk about skewed gates, I'm going to be changing the ratio of the NMOS and the PMOS transistor. So for example, let's consider an inverter where I've reduced the NMOS from 1 to 0.5. So in this case, the ratio of the width of the PMOS to the width of NMOS instead of being 2 is now 4. If you look at the pull-up resistance, the pull-up resistance in this circuit is going to be R, whereas the pull-down resistance is going to be 2R. So in this circuit, the pull-up is going to be faster and the pull-down is going to be slower. So we expect the logical effort of this gate to also change. And another peculiarity is we expect the logical effort to be different for the pull-up transition and to be different from the pull-down transition. So recalling the logical effort of a gate, the logical effort of a gate is given by the ratio of the pull-up or pull-down resistance of the gate times the input capacitance of the gate divided by the pull-up pull-down resistance of an inverter times the input capacitance of the inverter. So if you look at this case, if I look at the pull-up transition, for the pull-up transition, the effective pull-up resistance is R, the input capacitance at this input, instead of being 3, is 2.5. Compare it to an inverter, the normal inverter, to an inverter, it's going to be the same pull-up resistance R, however with the capacitance of 3C. So here, because we've reduced the capacitance to 2.5, the logical effort for the pull-up transition goes to less than 1, goes to 5/6. If I look at the pull-down transition, for the pull-down transition, the resistance is 2R with a capacitance of 2.5 divided by R times 3C. So here, the logical effort of the pull-down transition actually increases to higher than 1, going to 5/3. And so if you look at the average logical effort of such a gate, the average logical of this effort of this gate is slightly larger than that of the inverter, and it's roughly 1.25. So what you've seen here is the logical effort for the rising transition is less than 1, and it's better than that of the inverter. However, on average, this gate is going to be a slower gate compared to that of the inverter. Now, how much you skew the gates? Remember, it's a matter of playing out the pull down or the pull up resistance. So you can technically think that you can make them as uneven as possible. But the degree of skewing impacts the logical efforts, which is why you're doing this, but it also impacts the noise margin of the gate. So normally when we do skewing, we normally use up to a factor of 2. You can try larger than that, but you have to be careful about it because the noise margin of such a gate is going to be really poor, which renders it unusable. So in the schematic, we normally denote them as an H or an L, depending on whether it's skewed for a high transition or skewed for a low transition. And so if you think about a data path, if you want a specific transition to be fast, then you skew them in such a way that you cascade a high, low together, so that eventually you get one of the transitions through this path to be the fastest transition. So now let's look at an example of a few skewed gates. So the smallest inverter, say in our technology, is a 2-1 inverter, which has a pull-up and pull-down logical effort of 1 and an average logical effort of 1. Now, if I want to design the high skew of this inverter, we looked at it. We'll keep the size of the PMOS the same, but we'll reduce the size of the NMOS by half. So in this case, as we looked at the pull-up, so in this case, the resistance of pull-up is the same as that of the inverter. The pull-down resistance has become twice that of the inverter. Now, because of the fact that I've reduced the input capacitance at this node, the pull-up logical effort is reduced, and it's reduced to 5/6. The pull-down logical effort is reduced to 5/3, and so the average logical effort of this gate is 5/4. On the other hand, I can also do a low skew, in which I keep the NMOS as is and I reduce the size of the PMOS. So in this case, what you see is that the pull-up, so in this transition, because I've slowed down the pull-up transition, I expect the pull-up transition to be a slower transition, I expect the pull-down transition to be the faster transition. So the logical effort for pull-up works out to 4/3. The pull-up resistance is 2R with a net input capacitance of 2. So 2R times 2C divided by R times 3C gives us an LE of 4/3. The pull-down logical effort is going to be 2/3. So it's a substantial improvement over the inverter. And the average logical effort stays the same. If I look at a NAND 2 gate, so in a NAND 2 gate, under normal conditions, when we want to design a NAND 2 gate with equal pull-up and pull-down delays, we are going to design it as a 2-2-2-2 gate with logical efforts of 4/3 for both the pull-up and pull-down, and the nominal parasitic delays of 2 for both the rising and the falling transition. Now suppose I do the high skew where I want to skew the rising transition at the output, make the rising transition faster. I reduce the size of the NMOS transistors or make the pull down slower. So in this case, the pull-up resistance stays R, but with a reduced capacitance of 3. So I have R times 3C divided by R times 3C. So at this high skew gate, each input actually looks like you're looking into an inverter, and so therefore the logical effort of pull-up is reduced to 1. The logical effort for pull-down, on the other hand, increases to 2, because now you're seeing an input capacitance of 3 with the pull down resistance of 2R leading to a logical effort of 2. The average logical effort of this gate is 1.5. If you look at the parasitic delays, again for pull up the parasitic delay is 5/3, pull down the parasitic delay is 10/3, and the average parasitic delay is 5/2. So again here you see that because of the way that we have done the sizing, even the parasitic delay for the pull up is going to be less than the parasitic delay for pull down. If you look at the low skew on the other hand, where I'm going to slow down the rising transition of the output, I essentially have the logical effort for the pull up to be 2, the logical effort for the pull down to be 1. Again for pull down it looks just like an inverter. And so again here the average logical effort is 3/2. If I look at the parasitic delays, I'm going to have a switch of the previous case. So my pull up has a longer parasitic delay, the pull down has a shorter parasitic delay, and the average parasitic delay of this gate is 5/2. Let's look at the NOR2 gate. The NOR2 gate is sized as 4411 with an average logical effort of 5/3 and an average parasitic delay of 2. When I do a high skew of this gate, where I reduce the size of the NMOS transistors, I end up finding that the pull up logical effort reduces to 3/2 and the pull down logical effort rises up to 3, right? So you have a huge increase in the pull down logical effort. So therefore the average logical effort rises up to greater than 2 actually. And if you look at the parasitic delays for pull up and pull down, similar to the previous case, 5/3 for pull up, 10/3 for pull down, and an average delay of 5/2. Let's look at the low skew. In the low skew, these large PMOS transistors are reduced to 2 and 2. And so in this case, what you see is that the pull up logical effort goes to 2, the pull down logical effort goes to 1, and the average logical effort of this gate is actually 3/2, which is less than the average logical effort of the NOR2 gate. If you look at the parasitic delay again, parasitic delay is 8/3 and 4/3. The parasitic delay is the same as that of a NOR2 gate, symmetric NOR2 gate. And so what you see in this specific case, especially when it comes to NOR2 gates, the average LE of the low skew NOR2 gate turns out to be better than the nominal version, indicating that this gate might be better. So overall with regards to timing, you see that the low skew NOR2 gate actually will work faster than a symmetric NOR2 gate. And that is because of the fact that the PMOSs are large. So a small change in PMOS tends to dominate the performance, and therefore you end up finding a gate which is faster than the symmetric delay gate. So to conclude, asymmetric and skewed gates can be used to speed up circuits if we know additional information like the priority of the signal, or if you know that a particular transition is preferred over some other transition. The advantage is generally provided by increasing the delay of the non-critical edge. So whenever you have something critical and non-critical, there is a trade-off involved. So you speed up one at the expense of the other. Always keep in mind that unbalanced pull-up and pull-down networks need to be used with caution and need to be skewed carefully, else the sensitivity to noise will increase. So these gates have to be used very carefully and check the right skew so that you don't increase the overall impact of noise in such circuits.